pi k sigma. I want you to remember that. The electric field very close to a charged disk is 2 pi k sigma. When x is very small compared to the radius of the ring, this becomes, you see, that part will become 0 and the electric field will be given by 2 pi k sigma. Alright, we will be using that very many times. Okay? And using k equal to, do you remember? K equal to 1 over 4 pi epsilon naught. Can you replace that k by 1 over 4 pi epsilon naught? Your electric field becomes sigma over 2 epsilon naught. I will ask you for this in the next class. The electric field at a point very close to a charged disk is sigma over 2 epsilon naught, where sigma is the charge density on the disk. Alright. You know epsilon naught has a value given by that. You know that. I've given it to you earlier. Let's do a small problem. A disk of radius 2.5 centimeter carries a uniform charge density. This is sigma, 3.6 microcoulomb per meter squared. Using reasonable approximations, we have an exact formula, an approximation for large distances, an approximation for small distances. Find the electric field on the axis at a distance of 0.01 centimeter, 0.04 centimeter, 5 meter and 5 centimeter. Well, we got the radius of the disk is 2.5 centimeter, that is 0.025 meter. The surface charge density sigma is 3.6 microcoulomb per meter squared. And the formula we're going to use for the close approximation, the electric field is 2 pi k sigma. In part A, when x is very small compared to r, we use this approximate formula. So we got E equal to 2 pi k sigma. In other words, 2 pi times k is 9 times 10 to the 9. Sigma is 3.6 microcoulomb, make it to coulombs per square meter, and therefore the electric field is 2.036 times 10 to the 5 Newton per coulomb. We use the near point approximation. Tell me, how about B? What approximation we will use? Here again, compared with R, x is very small. Therefore, we can use the near point approximation, the same formula, which means the value will remain the same. You see, what that means is, if the disk is very large, it doesn't matter all over at points which are sufficiently close, the electric field will be all the same. So at this point also, E equal to 2 pi k sigma, which is the same as 2.036 times 10 to the 5. How about the electric field at 5 meter from the disk? You see, when the disk is very small, the radius is only 2.5 centimeter. It's smaller than the disk I'm holding. So 5 meter is very far. We will use the point charge approximation there. Since x is very, very large, that is 5 meter is very large compared to the radius, the charge Q is the point charge approximation. What is that? It's KQ over R squared. Q equal to A sigma, where sigma, we are only given sigma, we are not given the whole charge on the disk. So what is the total charge on the disk? If you know sigma, then Q equal to A sigma. Do we know the area of the disk? Well, if you know the radius, then we know its area. What is the area? Pi r squared. So Q equal to A times sigma, which is pi r squared sigma, and that will be pi times the radius squared, which is sigma, and the charge carried by the disk is 7.07 times 10 to the negative 9 coulombs. And we will use the approximation for large distances, which is the point charge formula. E equal to kq over x squared, that is 9 times 10 to the 9 is k. Q is 7.07 times 10 to the negative 9, and x equal to 5, and that is 2.55 Newton per coulomb. So we used in two cases the close approximation when x is very small, and in the third case x is very large. How about d part? Find electric field at x equal to 5 centimeter. It is not too small, not too large. You need to use the exact formula there. The electric field is 2 pi k sigma times 1 minus x over square root r squared plus x squared. So we use the normal distance formula and use all the given values. 2 pi times k times sigma, 1 minus x is 5 centimeter, 0.05 meter, over r squared plus x squared. R squared is 0.025 meter. Alright, replace r by 0.025, and that will give me 2.14 times 10 to the 4 Newton per coulomb. So if you notice here, we treated three cases. We had a long object, we obtained the electric field on the axis of that. We had a ring charge, we found the expression for electric field on its axis. And finally, we found the expression for electric field at a point on the axis of a disk. Now, you don't need to particularly worry about the derivations I gave, but you need to remember how to use the formulae for calculations. Alright, now what I'm going to do is develop Gauss's law in the next section and use Gauss's law to obtain these equations, which is a little more easier than using calculus. You can do away with calculus and use Gauss's law to obtain the same equations. We will do that in a later lesson. Alright, I will get back to you with the second part of this lesson a little later. Alright, until then, take care and do all the homework and try and do some of these on your own. Alright.